Hello everybody and welcome back. Root Beer here with more compass and straight edge constructions. I thought I'd show you how to do another regular polygon with circle and compass and straight edge. Okay. I keep saying circle because I see the circle tool and that's the one I use for my compass, but unlike my equilateral triangle and square videos, the 2 points that I give you, or that we start with, are not going to give us the side length of our pentagon. No. They're going to give us the radius of the circle we're going to inscribe it in. But we're still going to get a regular pentagon nonetheless. So, first things first, I want to construct a perpendicular radius to A, or a radius from A to the side of the circumference of the circle that's perpendicular to AB. So perpendicular bisectors to the rescue as usual. Okay, we'll connect those up. So the construction here is quite similar, I would say, to the construction if you saw my video on how to create the golden rectangle. Very, very similar. So we're going to connect this point up here to the midpoint of AB, just like we did to help create the golden ratio, the golden number, to create on our way to creating the golden rectangle. Now, why this eventually will produce a regular pentagon is not something I'm going to particularly talk about. The proof, at least the simplest one I know of, uses just a little bit of trig, some half-angle formulas. There's nothing I'm going to dwell on. I'm just going to show you how do we get regular pentagon. So I already have that circle. I need the other one, B to A. So we're going to get the midpoint of AB, and that's basically, if we think of AB as sort of 1, or the unit distance, then this midpoint here gives us a half. And this radius from A to the top of the circle is 1. And what we did to create the golden rectangle is we used this right angle triangle here. And then we sort of drew a circle and extended it out. That's not what we're going to do here, but we are still going to use this triangle here. We're just going to bisect this angle. So I'm going to clean things up just a little bit, get rid of some extraneous points. What don't we need? And I always forget about the points from zooming out. And I suppose we don't need this point here either. Okay, so we're going to bisect this angle right here. Well, we need to remember, how do we bisect an angle? Get a perpendicular bisector between these 2 points, and because of some nice isosceles triangle properties, I gotta make sure I hit the right one. There we go. So this perpendicularly bisects the length between A and this other dot here, but it angle bisects the angle here from this right angle triangle. Okay, so we get a nice intersection point between the vertical radius and this bisected angle here. And what are we going to do? Well, let's clean things up a little bit, because we're almost done actually. All we really need to do is now get a horizontal line going through this point. Okay, well, how do we do that? Or I guess I should, parallel to AB is what I really mean. Because I guess you could do this construction sideways and other things like that. So this will run perpendicular through this point, which is on a line that's perpendicular to AB. And that's what we want. We want a line parallel to AB. Okay, and this gives us an intersection point. Either one will do. They're both on the Pentagon. And now, second last round of cleanup, actually. So these points here are on our Pentagon. We can see that these two are equally spaced away from this height up here, because if I draw a circle to either one of them, whose center is the top point here, it does go through both of them. And we can actually use circles to find the other 2 points on our Pentagon. And now we really this is our final round of cleanup here. So now we really are at the end. We just need to connect these 5 points. So we get the line segment tool. I'll make it, I don't know, orange, I guess. And we have our orange regular pentagon. And this is a regular pentagon. We can even see from the circles that these adjacent points on either side of one corner are equally spaced apart. We can tell that from these circles. So this really is a regular pentagon. Quite nice. We'll undo those circles, because we don't need to really prove this. The technique does work. Other mathematicians have proved it. You can go ahead and prove it. As I say, it uses a little bit of trig, at least one of the techniques I know. Some half-angle formulas. I think half-angle for tangent, although I don't remember entirely. And there might be other ways to approach it that have half-angles for other things. But there we go. So, you know, equilateral, no, not equilateral, regular convex pentagon. We didn't use AB as the side length, but you can still see it all only depends on A and B. And I think that's pretty nifty. This is one of the more complicated ones. You can do 3, you can do 5, you can do a whole bunch of even ones. But the next odd-sided one you can construct, I believe, is the 17gon. Maybe I'll do that someday, but it's quite involved. And then after that, what else can you do? I think 257 is one you can do. And then I think there's one in the 60,000s, and that's all we know that can be constructed for odd-sided, regular convex polygons. Okay. But there we go. Regular pentagon. That's looking quite nice. So thank you guys for watching, and have fun creating your own.